Hey, and welcome back to another LeetCode video. We are approaching the end of our graphs list problems here on LeetCode.io. The two ones here that we didn't do, they are behind the paywall on LeetCode, but we have access to the word letter problem, which is a hard problem. So let's check it out. So I've tried this before 3 years ago. Hopefully I'll be able to do it again. So let's just have a quick read through this. So 127 word letter, a transformation sequence from word begin word to word end word using a dictionary word list is a sequence of words from begin words and then the intermediate words. The case such that every adjacent pair of words differs by a single character or single letter. Every word in the transformation sequence is in the word list that we're also given. Okay. Note that begin word does not need to be in the word list itself. And the last word is the end word in our transformation sequence. Okay, cool. Given two words, begin word and end word, and a dictionary of word list, return the number of words in the shortest transformation sequence from begin word to end word, or 0 if no such sequence exists. All right, so quick look at the constraints. All the words on the word list are unique. The begin word is not the end word. And all words consist of lowercase English letters. Nice. We're going to exploit this. And all words will have the same length as the begin word. That's nice too. And yeah, there's a limit on the number of words on the word list. We're going to ignore this for the complexity analysis. Otherwise, it's going to be of one space and time. Okay, and then the word length maximum is, well, the word is never empty. So cool. Okay, I think I have a grasp of the problem. Let's just go through an example. Here we are. That's a previous problem. Let's have a look at this one. Right. So we are starting with the word hit. And then the shortest transformation sequence from hit to cog is hit, hot, dog, hot, dot, dog, cog, which is using 5 words. So if we start at the word hit, well, since we're in the graph problem section, right, this is a graph thing. So what are all the possible next neighbors after hit? One would be hot, right? Do we have any other one? Hit? None. There are no other ones. Okay. What are the neighbors of hot? Well, obviously it's going to be hit, but that's going to be back edge, so we're not going to go there. Hot. Lot would be another neighbor. Just realized I drew the wrong edge, so the edge goes from hot to hit. The lot would be another neighbor. What would be another neighbor of hot? Well, dot. Dot would be another neighbor. And anything else? No, that's probably it. Now we continue this, right? Every word will have a couple of next words that we could go into. And we basically have to find the path that leads to the target word cog. So that's where we want to get to. And then we will have a path to it. Now, if we use a DFS approach, we might find a path, but we don't know if it's the shortest one. So we should probably use a BFS approach where we, well, if we flip this by 90 degrees, we'll basically have a tree structure. We have a starting word. Each word will have children words, like descendants that are mutations of the previous word. And then finally, we will have our target word somewhere down here. And then the shortest path is going to be that path and none of the other paths that we explore at the same time. So we should use a BFS approach where we go level by level. And then once we find the target node, we know that this is the path to the goal. This also means that we need to keep track of the words that we've visited, right? So we need to remember what lies on this path. What are these nodes? we not only have to find this path, we also need to remember what are the elements on that path. Yes. And let me just check. Well, actually, we're returning a number, right? So we're just returning the length of the path and not the elements. So we don't have to remember the elements. Okay, that's even better, because then the result will be just how many iterations we had to go in our DFS approach. So this would mean 1 iteration, 2 iterations, 3 iterations, this is a little example, and 0 on top. Cool, yeah, so we're going to use a BFS approach. Now, the other question is, well, we need to compute the next neighbors, and how are we going to do this? Are we going to iterate to our word list every time? We know we are going to assume that the word list is infinitely long. Of course, it can't be, but that's what we assume for our random analysis. So can we, well, constrict that, or constrict that somehow? Well, we can, because we know that we're only dealing with English case letters. So what we could do, so if we compute the neighbors of hit, we could, well, we know they're all the letters in the alphabet, A to Z. We could just start to mutate the first character of hit to all of the different characters that exist, and then check if the resulting word, that's a weird word, let's say sit, and we now just check if sit exists in our word list, and we just turn our word list into a set, so that we have O of 1 lookup. This is going to be 26 different tests that we have to try here, but we also have to basically, well, actually, are we saving a lot of time with this? Let me check. Oh, we can, well, if we had to try all the combinations of letters here, that would be 26 to the power of however many letters we have in our word, right? 26 to the power of something, something. So that's not awfully efficient, is it? But it would work. Or alternatively, we would just iterate through a word list. So that would be an O of length of the word list problem. So O of n to try all the different alternatives. That is also something we would try. So we could do O of 26 to the power x, which is the word length, or O of n, which means, yeah, we're going to iterate over O of n words at every single node. That's what we could do. Is there anything else we can do? Well, I assume we could also construct a trie from all of the words that we have. And if you remember, trie, like a prefix tree, that allows us to find words that have at most one character error in O of length of the longest word time, if I'm not mistaken. So that would probably be the most efficient solution. So yeah, with the getNeighbor method, maybe we'll try a couple of different implementations. So a third option is going to be a try. Right. So yeah, we have too many options, but let's just dive into that. And when it comes to implementing the neighbors method, maybe we have another look. So we will start with something where, well, if we start with the word list, and we're just going to turn it into a set. Word list is a set. And then, well, we're going to need our little queue for our depth first search. We're going to use a deck, collections.deck. And we're going to add the begin word to our little deck. You add it like so. You actually put it into an array. Begin word. And we're going to, well, we have to need to keep track of the visited set so we don't go backwards in our graph traversal. So visited is going to be a set. And then, well, we're going to iterate as long as we have elements in our queue. And we also need to keep track of our result. And result is going to be the length of the shortest path to the end word. Okay. Cool. So every time We think about this. Yeah. Well, we need to increase the result in the beginning. If our list of words consists of only one word, that is the end word, even then we're going to have at least one step, or sequence one length will at least be one. Or even if we have only one word, well, begin word is not equal to end word, but if it were the case, we still would have to do that, I believe. Now we iterate over all of the elements that are currently in our little queue, in range length queue, and we remember we can modify the queue, and it will not change, you know, the loop here, because length queue is evaluated once and only once before we enter the queue for the first time. So we will get the current word out, equals queue.pop left. Now, if the word is equal to the end word, we're done, right? End word. Well, we just return the result. Oh yeah, and let me see. So there is a case where maybe we can't reach the end word, and then we should return 0. So we should return 0 here at the bottom, because if we return a result here and we run out of queue elements, that means we never found the end word, and thus it's not reachable. So we need to return a 0 in that case. Right, so next we check if word in visited. Well, then you're just going to ignore this word. Otherwise, we need to add it to our visited set. Add word, and we need to iterate now over the next possible word. So for next in get next words, we can even reuse the word here, word for word, and get next words of word. We will have to add it to our queue. Queue append word next word. Yeah, we should probably call it next one just for clarity. Now we could also filter here. Well, actually, we do have to filter. We do have to filter here. If next word in not in visited, then we're going to append it. Otherwise, we would add a word that we already visited to our queue, which might result in result getting increased, even though we have no more places to go. So we could have all visited elements in our queue, result would get increased, and we would have an off by 1 error or something. But in that case, that means we didn't find the visited word yet, and we will never will. So maybe we don't need that. But I'm just going to put it here just for safety, I guess. And maybe we can test whether it works without in a moment. Right, so we need to implement the get next word method now. Def get next words of word. Well, how do we do this? Well, well, one approach was to, you know, go through all of the different words that exist. The word list. So here we have to, the option now for LeetCode, we have to go through all of 5,000 words to see which ones are possible descendants of the word. Or we go through, what is the maximum word length? Where is it? Word length, begin, word list length. So that would be 26 to the power of 10. I mean, that's both expensive. So maybe we should attempt, but I'm just curious whether the brute force way works, right? So if we were to iterate over all of the characters in the word, right? We could then iterate for letter or for J in range 26 for all the letters in the alphabet. And we could form a candidate word, right? Next words. Sorry, my mind is just seeing this, that I need to add this return. So we could say next could be, well, it could be the word, current word up to the character at position I. Then we're going to add the new character, and we're going to add the remainder of the word from here on. And then we check if next not in word list, which we turned into set here above, then we're just going to ignore that. And otherwise, we could, add next word to our word list. So append next. Now, how do we construct this? Well, the character is going to be the character of, we need to figure out what is the ASCII code of lowercase a plus j, right? So that's what this would be. That's how we would construct that word. I'm really curious if that is going to work. So let's do a little test here to see if it works on the test cases. Uninspected indent, okay, understandable. Collections is not defined. Oh, so we're just going to name this C and CHR. Oh, like that. So that is the function to get the character from the ASCII code. So we output a 0, but we expect 5. So why would that be? Oh, there's an off by 1 error here. So we actually have to add +1 here because we want to skip 1 character. And and we should probably filter out the original word as well, right? If next equal word, we should probably also skip it. To avoid an infinite loop where we convert word into word into word. And it's all the same. So that works. Nice. Let's see if that passes. Right, so that actually passes. Okay, that's surprising. Right. So in terms of space and time complexity, well, and some space, right? So what do we have in terms of space complexity? Well, we have our queue, right? So in the worst case, all the words in the word list are going to be needed to traverse through all of the, through the transformation sequence. So n is the length of the word list, so over n space in the worst case. Well, actually, no, that's not the worst case. Over n space is if every word in the word list is a mutation of the begin word. In that case, we would have a queue that contains all the possible combinations of words that are in the word list. But in terms of time complexity, well, worst case would be, we have to iterate through all of the words in the word list. And also our little get neighbors or get next words, our little get neighbors method, that's what that is. In terms of graph, if you think of graph traversal, that is going to be very expensive. So I think that's, well, you have 26 combinations per character, and then 2, whatever the length is of the words, right? So I think that would be the time analysis. Yeah, if you were to implement this with a try, could we even do that? Yeah, I think we could. We would just have to insert all of the elements in our word list into the try. Actually, let's do this with this example here. I'm just going to copy the example again. And maybe we don't put that into code. Maybe I'll leave that up to you. But let's just sketch out the solution. Right. So what we have here is we have, well, if we constructed a try, right? So we have the try, and at the root level we will have all the first letters of that we have from the letters in our word list, and yeah, from the word list. So we would have H, we would have a D, we would have an L, and a C. So that would be the list of children of the root of the try. And then after H, the children are just O. And then that child would be G. Wait, hot, a T. Would be a T. Now for D, we have dot and dog. So we have an O. And then we have a T and a G as the children of that. Dog and dot. And for L, it's lot and log. So we have the O here and also a T and a G. And for cork, we just have O and G as the nodes in the subtree. So yes, and now if we want to find all of the successors of hit, it means we're going to search for a path in this try where we allow at most one, well, where we require exactly one modification. So, and we can have this modification at any place or at any level in our try. So we would start with hit. And well, we can say, okay, we're not going to have an error here. So we're just going to go down here. So we're going to pass the H. Now here we'll have an error where I is not the same as O. But then we have another matching one. So reach the end. So actually, hot is a possible transformation of that word. Now, another case could be where we try to say, okay, we allow that the first character is a mismatch, so H and D are mismatched, but then we are running into a second mismatch here where I is unequal to O, but we've already used our one required hit here. And if we had the word hot hit, let's say hit, in this try as well, just to illustrate, so if we have I here as well and a T here, just hypothetically, this path would not be allowed because it doesn't have any defects as we go down. So we H is a match, I is a match, and T is a match. So this one would also be not a valid mutation of our word hit. Yeah, and you could do this now well, you do this for all of the possible combinations. And that should significantly reduce the number of operations to determine what the next neighbor is. Yeah, and I would recommend that you implement this to try it out. So you would probably have something like this: get create try, and and then you get next would then be the traversal thing that we have here. And you need to create the try one time. Get next words, maybe you give it the try and you add a little t equals good try. Why is it true? Try, and then get next word, you pass on the try and try. That is the try. Well, maybe I should try to flesh it out. Why not? For word in word list. Now, I'm going to use a default dict here, and it will have a list. Collections.default dict list. Well, yeah. Or let's see. Yeah, we should do it like this. So now what we do is for C in, we're going to get the handle of the root of the node. Is right for C in word. You're going to say, well, T at C equals, what is that? Well, maybe I shouldn't use the default dict here. I'm just going to do this. So if C not in T, well, we're going to add it. C equals a new list, and then we're just going to say T equals at position C. So we're inserting all of the letters of the character into our try until we ran out of characters. And then at the end, we just return it. Return a try. And now our get next word is pretty much, the try traversal, where you just do the search. So what you do is you say how should we do this? Well, we need to have some kind of a DFS approach here. Get next word. So maybe we need a little helper method to traverse our little try. So what we would say is build try. So find mutations. We're going to pass in a try. We're going to pass in a word. We're going to pass in an index. We don't have to pass an index. We can do it iteratively. And we say, what is the maximum number of defects? Well, max defects is defects equals 1 that are allowed. And this now looks the same as our get words. So why don't we use that one? So yeah, we want to do it iteratively. So t equals try. And then we do for Well, let's think about this. I'm kind of struggling to come up with the recursive, with the iterative implementation right away. What would a recursive one look like? Well, if we had a match function, we had the level of the try, we had the word, we had the index, we had the defects counter. So, and then we check if idx larger or equal than length of words. That means we're basically done. Well, we also have to check, the path. So the current word that we're building up, path, that needs to be listed. If defects equals 0, well, we're going to add this to our result list. So we also need to pass in the result. In that case, we're going to say result.append path, which is a copy of the path. Well, actually, we're just going to join the elements of the path. That's going to be the word. Join the characters on the path. Right. Else, if well, if defects is smaller than or let's say, well, if you count the defects, we only allow it when it's 1, right? If defects is larger than 1, we're not going to do anything, right? We're basically going to ignore that. If defects larger or equal than 1, then we return it. And if defects equal than 1, we're going to append it. Otherwise, well, we're going to do our usual stuff. And we're just going to return the result otherwise. So, right. We can also, well, we need to check if defects is smaller or equal than 1. Then we perform our check. If defects is equal to 1. Yeah, I think I'm making things more complicated for myself than I really need to. Right. So if defects is 1, if defects larger than 1, we're just going to return. There's nothing to do here. If the length, if we found the length of the word matches, then we're just going to check if the defects is actually 1. Otherwise, we're not going to return anything. So we're just going, well, not returning anything is wrong. We're just going to return the result. Otherwise, it's an invalid. And now what we do is for character in T, those are all the possible next characters. And if the next character is unequal to the character at word idx, then that means we're going to increase our defect. So what we'll do is we'll call the recursive is match on t.c. So that's the next level in the try. We're going to pass in the word. We're going to pass in idx plus 1. We're going to pass in defects plus 1. We're going to add in the path and the result. Now, the path we have to extend it, right? What we do is path.append the character, or path.pop character after we've done the recursive thing. Now the other case is if c is equal to the current word, well, we still do the same thing, except that we're not increasing our defect counter. So, and then in the end, we just return the result. Now I can optimize this a little bit that I struggled with before. Yes, so this will be an else statement here. Right. If the number of defects is larger than 1, well, there's nothing for us to do. Otherwise, if the index has reached the end, then we're going to add the current path to our result set. If defects is not 1, then that means we didn't have any, so we're not going to consider this word. And well, if neither we've reached the end nor we've exceeded the number of defects, then we're just going to try to go through the try further. So in our get next words, what we do is, well, get next word, that is going to be our little result. And we're just going to call our isMatch function with all of these parameters. We pass in next words as our result set, right? We're going to start with word. We're going to start with the try. We're going to start at index 0. We're going to start with 0 defects, and we're going to start with an empty path. So that is pretty much that. And we don't actually have to define next words here. We can just return this. Return try. So turned out we actually needed that little get next words helper function to start initializing our recursive call. So I'm kind of scared to run this now because I have not tried this. I have no idea if this is going to work. It probably won't, but let's see. So closing parentheses too many. Another typo, build the try. Let's run this again. Let me see. Okay, lose the colon. Indices must be integer slices. T equals build try. List indices must be integer slices, not string. EC equals. If C not in T, well, the try is, oh, of course, we have to create a hash map, not a list. Okay, string object cannot be interpreted as an integer. So let's see, IDX, popc, path. Path is the list. So that is a list. Path pop, path append, path pop. Why is this not considered a string? Path append C, path, path, path. This should be correct. But maybe are we doing the result append here? Return the result. Checking. If match effects +1 path result. Let's just, yes, let's just check if we get the parameter order correct. So try word index defects, try word index defects, path result, path result. So that looks good. That looks good. String object cannot be interpreted as integer, path pop C. Right, why do I pass in a parameter? Well, I just need to pop the last element from it. Cool, okay. Oh wow, okay, so that seems to work. Well, now in terms of time and space, well, to store all the words in memory, well, by the way, the space analysis before, I think, was slightly off because we still need to account for how many characters are in each word. So the space is actually off n times m. Now for the try, that should bring down the complexity to whatever the branching factor is in our words try, and however how deep our try is. So we would have an n to the power of what is the maximum branching factor in our try. But the branching factor is going to be much lower than, with 26 characters. I think I also did the analysis the wrong way. So it wasn't 26 to the power something, was confused. What did I have before? Yeah, it should have been m to the power of 26. So yeah, so now we have m to the power of whatever the maximum branching factor is. And the branching factor would depend on how many different words we have, right? However, this is only this, in the worst case, this is only in one layer. So I don't know exactly what the time complexity is for a try that has n elements of length m in it. Yeah. So you would have to, I guess, Google that, and then you would know what that complexity is. Note to self, I have to get a little bit better with these branching factor considerations for runtime and space analysis stuff. Let me think. I mean, in the worst case, we're going to visit all of the nodes in the try when we go through it, right? So actually it would be of n times n time, wouldn't it? Well, you tell me. I'm not 100% sure. Room for improvement. But yeah, both approaches work, which is nice. And that should finish off the last problem on our word ladder list. And yeah, let's think about what we should tackle next. Maybe we should continue with the dynamic programming ones.